What if I told you there is a place in our solar system where it rains diamonds? Not metaphorically, not as a figure of speech. Actual carbon diamonds, millions of carats in size, falling like hailstones through an ocean that has no surface, inside a planet we have visited exactly once in all of human history. And that same planet, the one raining diamonds, the one we almost completely ignore, has winds that would tear apart every structure humanity has ever built in under a second. Supersonic winds. On the coldest planet in the solar system, a planet so far from the sun that it receives 900 times less sunlight than we do, and yet somehow generates more heat than it takes in. That should be impossible. The physics should not allow it. And yet, there it sits, at the edge of our solar system, quietly violating the rules, hiding a burning black ocean beneath the most deceptively calm blue exterior in the known universe. This is Neptune, and almost everything you think you know about it is wrong. Most people write Neptune off. It sits at the far edge of our solar system, a pale blue smudge that barely registers in conversations about space. We talk about Mars colonization, Saturn's rings, Jupiter's monster storms. Neptune gets a footnote. But that indifference is a mistake, because when you actually examine what is happening on and inside that planet, you realize it is operating by a set of rules that should not work. It defies the physics we rely on to explain every other world we have ever studied. This is not a frozen, quiet outpost. This is the solar system's most violent secret, dressed up in a coat of soft blue clouds. Here's something that almost nobody knows about Neptune. Before any human eye ever confirmed it existed through a telescope, mathematicians had already found it using nothing but arithmetic. That fact alone should tell you something about how unusual this planet is. It announced itself through the misbehavior of another world. In the early 1800s, astronomers were carefully watching Uranus move across the sky, charting its position, comparing observations against Isaac Newton's gravitational equations, and Uranus kept getting it wrong. It would speed up when it should slow down. It would drift off course in ways that made no sense unless something was out there, something massive exerting a gravitational tug from the darkness beyond. Two mathematicians on opposite sides of the English Channel, Urbain Le Verrier in France and John Couch Adams in England, independently sat down and attacked the problem with pure mathematics. No telescope, no observation. Just equations, orbital mechanics, and an extraordinary belief that the math would lead somewhere real. Le Verrier mailed his predicted coordinates to the Berlin Observatory. The astronomer Johann Galle pointed his telescope at that exact spot on September 23, 1846. Neptune was there, less than 1 degree from where the math said it would be. We found an entire world the size of nearly 60 Earths using ink, paper, and human reasoning. And then, for the better part of a century and a half, we mostly left it alone. We have visited Neptune exactly once in all of human history. One single encounter, and calling it a visit is generous. In August of 1989, Voyager 2 completed a 12-year journey across the solar system and had a few short hours to study Neptune before being permanently flung into interstellar space. A few hours for a planet we had waited over 140 years to see up close. But those hours changed everything we thought we understood. Scientists going into that flyby expected silence, expected stillness. At Neptune's distance, sunlight is roughly 900 times weaker than it is here on Earth. The logic was simple and seemingly airtight. Weather requires energy, energy comes from the sun, less sun means less weather. Neptune, they believed, would be a graveyard, a cold, static, featureless atmosphere with nothing to show but the bleak emptiness of distance. Voyager's images arrived and the scientific community had to completely rebuild their assumptions from scratch. The first thing that jumped out was a storm, a massive churning anticyclonic system called the Great Dark Spot, big enough to fit the Earth inside it with room to spare. It looked like Neptune's answer to Jupiter's Great Red Spot, a permanent atmospheric scar driven by the planet's internal fury. Scientists were stunned. Then, 5 years later, the Hubble Space Telescope looked at Neptune again and found that the Great Dark Spot was simply gone. Not weakened, not smaller, gone. Jupiter's famous storm has been raging for at least 400 years. Neptune's disappeared in half a decade. That tells you something terrifying about how fast that atmosphere is moving, how violently it churns, how little stability exists on that world. The winds Voyager measured were not just fast, they were supersonic, over 1,200 miles per hour, the fastest winds ever recorded anywhere in the solar system, on the planet receiving the least solar energy of any world in our neighborhood. Pause on that contradiction for a moment. The coldest, most sun-deprived planet we know of is simultaneously the most aerodynamically violent. Every intuition you have about how weather works says this should be impossible. And yet, there it is. So where is the energy coming from? If the sun is not powering those winds, something else must be. The answer forces you to abandon the comfortable image of Neptune as a frozen, passive world, because Neptune is generating its own heat. It radiates more than twice the energy into space than it actually receives from the sun. Something inside that planet is burning. Not metaphorically. The interior of Neptune is a genuine heat engine running on two possible fuel sources. The first is residual thermal energy from the planet's formation 4.5 billion years ago, heat that has been slowly leaking outward ever since, trapped by the planet's sheer mass. The second is even more dramatic, a process called the Kelvin-Helmholtz mechanism, where the planet is actively contracting under its own gravity, the outer layers slowly collapsing inward, and that gravitational compression generating friction that converts into enormous quantities of heat. Neptune may be very slowly crushing itself, and that self-compression is what drives its surface into chaos. Now comes the part that genuinely sounds like science fiction, but has been confirmed in a laboratory. If you could somehow survive the descent into Neptune and travel downward through its atmosphere, the first thing you would notice is that the concept of a surface simply does not exist. There's no moment where the sky ends and the ground begins. The hydrogen and helium atmosphere just gets progressively denser and hotter as you sink deeper, until you cross a threshold where gas and liquid become the same thing. Scientists call this state a supercritical fluid, and it is exactly as strange as it sounds. Imagine an ocean with no surface tension, no clear boundary between liquid and vapor, a scorching, dense soup that behaves simultaneously like both. That is the mantle of Neptune. Thousands of miles of electrically conductive, superheated fluid made primarily of water, ammonia, and methane, all compressed into a single roiling mass. Go deeper still, around 4,000 miles beneath those blue clouds, and the pressure climbs to millions of times what you experience standing on Earth at sea level. The temperature approaches 7,500 degrees Fahrenheit. At those conditions, the methane molecules that give Neptune its blue color get destroyed. The carbon and hydrogen atoms that form methane get ripped apart from each other, and the isolated carbon atoms, compressed under that unimaginable weight, begin to crystallize. They form diamonds. Actual diamonds, likely millions of carats in size, precipitating out of the fluid like hailstones and falling downward through the mantle toward the core. This was a theoretical prediction for years. Then, researchers at the SALC National Accelerator Laboratory used high-powered optical lasers to compress plastics to Neptune-like pressures in a laboratory setting, and they watched nanodiamonds form in real time. The diamond rain is real. And it does more than just sound spectacular. As those dense diamond crystals fall through the fluid mantle, they generate friction. That friction converts gravitational potential energy directly into heat, feeding back into Neptune's internal engine and keeping the whole violent system running. What waits at the very bottom is stranger still. At the deepest accessible layers of Neptune, surrounding whatever rocky nucleus exists at the absolute center, water stops behaving like water in any form you would recognize. The pressure at those depths forces oxygen and hydrogen atoms into a configuration that has no equivalent in everyday life. The oxygen atoms lock into a rigid crystalline lattice, a solid. But the hydrogen atoms, rather than locking in place alongside them, flow freely through that rigid oxygen framework like a liquid moving through a solid mesh. This state of matter is called superionic ice. It is black, it is hotter than the visible surface of the sun, and because those hydrogen atoms carry electrical charge as they flow, the whole structure is electrically conductive. This black, burning, solid liquid hybrid material is almost certainly the engine behind Neptune's magnetic field. And that magnetic field is every bit as chaotic as everything else about this planet. It is tilted 47 degrees away from Neptune's rotational axis. It is offset from the geometric center of the planet. It is not the clean, organized magnetic shield that Earth generates. It is a lurching, asymmetric, constantly shifting bubble of magnetic force generated by ice that is simultaneously solid, liquid, and on fire. And then there is Triton. If everything about Neptune's interior represents physics pushed to extremes, Triton represents gravitational history written in the most violent terms imaginable. Triton is Neptune's largest moon, and it orbits backwards. In a solar system where nearly every moon, every planet, every ring system rotates in the same general direction as the sun's original spin, Triton goes the opposite way. That retrograde orbit is not a quirk, it is a confession. Moons that are born alongside their planets share their planet's orbital direction. A moon going the wrong way was not born there, it was caught. Triton was almost certainly a Kuiper Belt object, a dwarf planet similar in nature to Pluto that drifted too close to Neptune billions of years ago. Neptune's gravity captured it, but that capture was not gentle. The gravitational interaction that snagged Triton almost certainly shredded whatever original moon system Neptune had built up over its first billion years of existence. Those original moons, gone, replaced by this interloper orbiting defiantly in the wrong direction. The capture also melted Triton's interior through tidal heating, and even today, Voyager spotted the consequences: active nitrogen geysers erupting from the surface and spraying material 8 kilometers into the sky. Triton is frozen on the outside and still processing heat on the inside, a captured world that never fully recovered from its violent arrest. But Triton's story ends on a timeline that reframes everything. It is not in a stable orbit. Every year, Neptune's gravity pulls it fractionally closer. The math is already written. Millions of years from now, Triton will cross what is called the Roche limit, the distance at which tidal forces overcome the structural integrity of a moon. Neptune will tear it apart. The material will spread into a ring system potentially as dramatic and visually spectacular as Saturn's. Neptune is going to build itself new rings out of the moon it captured and destroyed. That is the scale of what this planet does. So when you see photographs of Neptune, that serene, almost meditative blue sphere hanging in the dark, understand what you are actually looking at. You are looking at the exterior of a world that is raining diamonds onto a core of burning black ice, where an ocean has no surface and gas has no ceiling, where winds that would shred any structure ever built by humans are the atmosphere's normal resting state. You are looking at a planet that destroyed its own moon system and replaced it with a captured dwarf planet that it now slowly dismantles. You are looking at the only planet discovered by mathematics before it was confirmed by human eyes, a planet that told us it existed through the gravitational trembling of its neighbor before we ever pointed a camera at it. We went there once, for a few hours over 30 years ago. The data from those hours is still generating scientific papers, still producing unanswered questions, still revealing how much we do not know about a world sitting in our own solar system. An orbiter mission to Neptune is technologically feasible right now. The engineering is understood. The mission has simply never been prioritized, which means everything you have heard today represents our best guesses built on a single afternoon's worth of data from a spacecraft that has since left the solar system entirely. Neptune's core, its full atmospheric dynamics, the exact nature of its superionic layers, all of it remains unconfirmed at the level of detail we have for every other planet we have invested in studying properly. That pale blue dot is holding secrets that no instrument on Earth can penetrate. If you want to know what this solar system is truly capable of, Neptune is the answer, and we have barely started asking the questions. If this made you look at the solar system differently, you might want to watch the video on why Uranus is far stranger than its reputation suggests, because the story of how we figured out these outer planets is just as bizarre as the planets themselves.